All right, so let me ask you a question. What do physicists, air traffic controllers, and, get this, high-end video game creators all have in common? I know, it sounds like the beginning of a weird joke, right? But the answer is actually a super powerful mathematical tool that they all use to make sense of the world. Just think about that for a second. We've got people charting the stars, people guiding massive airplanes through the sky, and people building entire virtual realities. On the surface, those jobs couldn't be more different, but underneath it all, they are all using the exact same secret language, a language that describes movement, force, and where things are in space. So what is this incredible language? Yep, vectors. That's the whole secret. It's a simple word for a really, really profound idea. So let's break down exactly what they are and, more importantly, why they're such a big deal. But before we can really jump into the deep end with vectors, we have to start with something a little bit simpler. Something that, honestly, you already use every single day, probably without even realizing it. We need to talk about scalars. So, what is a scalar? It's really just a simple number. It's a quantity that only has magnitude, which is just a fancy way of saying it tells you how much of something there is. No frills, no direction, just a plain old amount.
For instance, the distance from you to that park bench over there. Let's say it's 10 meters. That's a scalar. Or the amount of coffee in your mug, maybe 300 milliliters. That's a scalar too. Even its temperature, say 60 degrees Celsius, you guessed it, also a scalar. They all tell you how much, and that's it.
Okay, so we've got scalars down. Now it's time to level up to vectors. And the leap is actually not as big as you might think. We're really just adding one more crucial piece to the puzzle: direction. So here's the absolute key difference. A scalar only has magnitude, right? Well, a vector has both magnitude and direction. The classic example to make this stick is the difference between distance and displacement. Distance is a scalar, but displacement, which is just distance in a specific direction, that's our vector.
Let's go back to that bench for a second. Knowing it's 10 meters away isn't really enough to get you there, is it? I mean, you could walk 10 meters in a circle. You need to know it's 10 meters that way. And that combination, the 10 meters and the that way, that's your vector. That's your displacement.
Okay, so vectors have magnitude and direction. Got it. But their real superpower, the thing that makes them so essential in physics and programming, is a slightly tricky-sounding property called coordinate invariance. But really, it's all about your point of view. And this quote just nails it. What makes a vector truly a vector is that the actual thing it's describing, a force, a movement, doesn't change just because you decided to look at it from a different angle. The underlying reality stays the same. Let's make this really concrete with a little thought experiment. Imagine you and a friend are moving a heavy tent. You're on opposite sides of it, so you're facing each other. From your friend's perspective, to move the tent, they take 2 steps to their right and then 3 steps forward. Simple enough. But from where you're standing, facing them, you have to do the complete opposite to move the tent in the same direction. You have to take 2 steps to your left and 3 steps back. So it feels like you're doing 2 totally different things. Now, if we write this down mathematically, it looks different too. Let's say your friend's point of view is a normal X and Y grid. Their movement is the array 2, 3. But because you're facing the opposite way, your grid, your coordinate basis is flipped. So your movement looks like the array -2, -3. The numbers are literally the opposite of each other. So how can these opposite numbers describe the same thing? Well, this quote explains it perfectly. Think of the array, the 2, 3, as just letters. The basis, your point of view, is the language you're speaking. But the vector is the actual meaning behind the words. So even though your arrays, your letters, are totally different, when we add the context of your different points of view, your languages, we realize you're both communicating the exact same meaning. You both moved the tent the exact same distance in the exact same absolute direction. The vector, the physical movement, was identical. That is coordinate invariance, and it is an absolute game changer. Now, this powerful idea of an object staying the same no matter how you look at it doesn't stop with vectors. It's actually the key feature of a whole family of mathematical objects called tensors. Vectors are really just the first step into a much bigger world. And that leads to a natural question, doesn't it? If a scalar holds one piece of information and a vector holds 2, is there something that can hold even more? Can we pack more complexity in? Oh, absolutely. The answer is tensors. The best way to think of them is as a big family of things that are all defined by that same coordinate invariance we just talked about. The rank of a tensor just tells you how complex it is. A simple scalar, that's just a rank 0 tensor. A vector, with its magnitude and direction, that's a rank 1 tensor. And believe me, it keeps going up from there.
And this isn't just theory. Let's go back to that video game designer. To make realistic-looking water, it's not enough to know a force hit the surface. You also need to know the orientation of that force. You have to combine two vectors, the force and the orientation, and what you get is a new quantity called stress. Stress is a second-order tensor, and it's what allows the game engine to create those incredible, realistic-looking waves and whirls.
So we've gone from simple numbers all the way up to these complex tensors. And I know it can seem a little abstract, but these concepts are literally the foundation for some of the most advanced and incredible technologies we have today.
I mean, higher order tensors are absolutely essential for running massive scientific simulations. They're used to design the aerodynamics of modern cars, and they're even used in a medical technique called diffusion tensor imaging, which lets us map the incredibly complex network of wiring inside the human brain. When you boil it all down, that's what these tools do, from the simplest scalar to the most complex tensor. They give us a consistent language to make sense of ridiculously complex interactions in a way that stays true no matter our point of view.
And that really is why they are so foundational. They're not just abstract math. They are a perfect, shining example of the elegance, the beauty, and the pure fundamental usefulness of mathematics in describing the reality of our universe, a secret language that once you learn it, you start to see everywhere.